All right, in this video, I'm going to show my Electrical 1 students different methods of finding out the values within a given electrical circuit. Now, this top portion here is how we teach it in our courses, and the reason why is we generally give you very basic circuitry. That's the level of this course that we're teaching. And also, if we gave you any more advanced methods, which are far more robust and can handle significantly more involved circuitry, you wouldn't have the mathematics behind you to do it. So there's certain math prerequisites for this course, and what you will eventually need if you get deeper into this is a good grasp of the area of mathematics called linear algebra, also known in some circles as matrix math. And although some of you may have that, it's not a prerequisite for our Electrical 1 course. So I am going to show you how to do it with linear algebra, and it's actually how computers do these types of calculations. So you've seen circuits that I've drawn up using software, and you may have wondered how these electrical stimulation software programs calculate all this information. And it is by way of linear algebra. So that's what I'm going to show you here. And as a bit of an aside, linear algebra is literally the mathematics of everything we do in the world. I don't think there's a single thing you can't calculate with linear algebra. So we're speaking doing statistics, PCA, principal component analysis, linear regression. So you've got a signal, for example, with some noise, and you don't know the quantity of that noise because it is a statistical calculation. It's not something that is known. It's just known from statistics. And so, for example, you're taking a bunch of measurements and you know you're going to be out a little bit here and there. It could be physical measurements of anything. And you'll use linear algebra, and what it will do is it will give you your best fit to the data. As a matter of fact, that's what it's called, best fit or linear regression. It'll give you a best fit to the data while minimizing all of the errors in the groups of calculations. So it's just everywhere, linear algebra. Also, Google PageRank. So who gets to be at the top other than if you're paying? Right? That's done using linear algebra. You watch movies on Netflix, and Netflix gathers the movies you watch. How can it determine what movies you're likely to like next? So it will offer them to you. That's linear algebra. You might not be aware, but absolutely everything sent across the internet, the airways, is compressed. So we can call that lossy compression, you may have heard. So a JPEG is a lossy type compression. And what that means is you take a raw image, which is maximum file size, and what the JPEG format does is it runs it through its algorithm, and it's specifically designed for general images. You might not use it, or you wouldn't use it for seismology or trying to maybe send radio transmissions because they have their own characteristics. But an image or a video in JPEG type format, there's rather smart formats, or you may have heard them called in video formats codecs. Okay? And those are the algorithms that determine, given the type of data that they're going to be sent, what is the best way to compress those images and yet, or audio tracks, for example, and yet still have them viewable or have them sound like they are the full file with no compression, because the internet would run awfully slow. You wouldn't be able to watch your television without large amounts of glitching, and none of that would work. So these are all these tricks that are used to get that data compressed, sent to you, and viewable or listenable in a way that you don't even notice data has been lost. And that's all done with linear algebra. So let's get right down to it. So I won't spend much time on this top half because this is how you have been taught to do this most basic of combination circuits. So we have R1 in series with R2 and R3, which are in parallel with each other. Okay, so we set up our table like we always do, the voltage, current, resistance across the top, R1, R2, R3, and our totals along the side. And the first thing you always do almost always in our class is calculate RT. So it's R1 plus R2 and R3 in parallel. So that comes down to 12 ohms. Once you have 12 ohms and you know VT is 12, you have 1 amps. You recognize that I1 is the same as IT, so you can put that there. From there, you get V1, 10 volts. If you have a 10 volt drop from 12, you have 2 left across the parallel section. So it's 2 and 2. You do over here, you need just to find I2 and I3 left. I2, just simple Ohm's law, V2 over R2, third of an amp. And I3, V3 over R3, 2/3 of an amp. And you are done. Very, very simple. Now, where this type of process actually tends to reach its limitations is when this circuit gets significantly more complicated. Maybe you have another power source. That's not something you see in our course, but you will find it. If you have another power source down here, you really run into a limitation doing it this method. So how would a computer do it then? And that's where I bring you to this same circuit, and we're going to go through it in a manner that a computer would using linear algebra. And just before we get into that linear algebra, I want to, we'll stop here and we can branch. So if you don't know linear algebra, this is not going to be a linear algebra course, but I'm going to explain to you how you can see what's going on. You don't want to go that far. You can use this and type it into a free online resource, and it will give you the same information. So what we're doing here is we're trying to find the currents. This is what we're doing first in this method. Now, there are multiple methods using linear algebra to do this type of thing. But we're going to use what's called the mesh process, or also the loop. You may even hear it termed the branch, because these are different branches of this one whole circuit. But it's mesh or loop typically is what you're going to hear. So what you're trying to do is find the current in the individual loops that you have in your circuit. So if you are able to identify the smallest individual loops in your circuit, you've got half the battle done. So you can see here in red, this is one loop right here. I just called it IA because I don't want to call it I1 because I don't want to confuse it with the current through resistor 1, although it happens to be the case in this case. So you can pick an arbitrary direction. It doesn't matter if you're wrong. And we typically calculate these things always with conventional current flow, as you know. So I always do mine in the expected conventional current flow. We're going to know in this circuit right here, we know it is this way. On other parts of the circuit, depending on the complexity of the circuit, you actually might not know. But it won't matter if you draw your arrow clockwise or counterclockwise, because all that's going to happen is if you find out you've chosen the improper direction, your answer is just going to come out negative. And everyone understands that negative means you've got your polarity wrong or the current's flowing in the opposite direction. So that's not a big deal. So here's one small loop. I've termed it IA. Here is another loop, the second, in this circuit, IB. Now, this larger loop, it is a loop, but you don't count that because you cannot count loops within loops. And if you can make smaller loops out of this larger one isn't counted. So you can see there's 2 loops here. 2 loops means you're going to have 2 equations. So loop IA. Here's what you want to do now. You have the resistance, which is known, and a current, which we're calling IA. So you know if you do IA times R1, you're going to have the voltage across here. And each of these loops are going to relate to R times I will equal voltage. You know that's Ohm's law. So loop A, what you do is you take all the resistances in this circuit, or the loads. So it's a 10 ohm and it's a 6 ohm. So 10 plus 6, that's the total resistance of that little branch circuit. If you multiply it times IA, you're going to get the voltage for that circuit. Now, that's what you have here. Now, there's a little term over here that we need to discuss. Notice that R2 is special, and it's special in the fact that R2 is part of IA loop and IB loop. So we have to treat that one a little different. We have to watch what we're doing there. So the current flowing in this direction, there again, one arbitrarily chosen, and I chose it to go in conventional current flow. It's going to make your life a lot easier if you just maintain the same format throughout. So it is 10 plus 6 times IA. Now, look at this loop here that I've got going on here, IB, because R2 is part of that circuit. So we have to have a term in there for R2. Now, I've got it going again in this direction. But if you'll notice, on the IA circuit, the current is flowing this way. On the IB circuit, it's flowing the other way. So the IB portion of this is minus because it's current going against the flow of IA. So it's minus 6 times IB. It's just what we've done here. And what is the power source in IA? It is 12 volts. So you make it equal to 12. You do the same thing with IB. So it is, I should back up here for 1 second. You notice it's going to make it easier if you put all your IAs on top of each other and IBs on top of each other. For these two equations, loop IA and loop IB, it doesn't actually matter if you do it here. Just note, when we get to the linear algebra, you have to keep your IAs and IBs stacked on top of each other. So in this case, what I wrote first is IB, and then I just filled in IA later. So we'll start here, but understand, I could have put IB before IA. It would work out to the same thing. You would just have to make sure you arrange it properly when you get to the linear algebra portion. But let's not go there yet. So IB is 6 plus 3 plus 6, times IB, okay? And there again, you have to add this to it, the IA times 6 term to it, which is here, but it's flowing in the opposite to IB, so it's a negative. And is there a power source here? No, there is not. So you make that equal to 0. Now, if you don't want to use linear algebra or you don't know how, I'm going to show you a trick here, and we're going to go to the internet to a free site that using these two equations, you're going to get straight to the same answer. And by the way, the back end of this website that we're going to, Wolfram Alpha, does do it this way, but it can do this for you. So you just can punch these things in. If you don't know how to use linear algebra, or more specifically, if you don't have a program that you can type this in, just go to Wolfram Alpha. It basically does it all on the back end for you, and you don't have to know any of this. So let's head on over to Wolfram Alpha with these two equations in hand. All right, so we are on wolframalpha.com. And what you do is you take those two equations and you just type them into this bar here, separated by a comma. Now, you'll notice I had IAs and IBs in the equation. Okay, we have to substitute that IA and IB for some variable, some letter. So I chose X and Y. So your IAs are all X's and your IBs are all Y's. And you type that in, again separated by a comma, hit the enter or the equal, and it spits out a solution for you. And it says X equals 1, Y equals 2/3. So remember those, we're going to use those. So X would be IA and Y would be IB. And what it's actually done, let's just take a peek down here at this XY graph. By the way, is why I used X and Y, because what it does is it plots these two equations on the XY graph, and where they meet is the solution to this equation, and it will give you those two currents. That's how linear algebra works. You can see it there, 1 and 2/3. So it actually plots this for you, which is very nice. So once you have these, you can go back over to your worksheet, which is what we'll do now. But I just wanted to show you, this is a free site. You can pop in equations. It gives you solutions. It plots things as it can, and a lot of other information that you may or may not need that goes along with it. It's a free site. Most of you have probably seen it or heard about it before. So let's move on over and complete this as if we were using linear algebra itself. And remember, 1 and 2/3. All right, so now we're over back to our worksheet. And this is what linear algebra looks like. You're dealing with matrices. And what we need to do is to put these two equations into matrix form. And understand what we're doing. We're just doing it R times I equals V. This is what's going on here. Now remember I had mentioned that you have to have all your IAs and IBs stacked on top of each other. So they have to be in their own respective columns. So the first equation is this one right here, and the second equation is this one. So you'll see this is 10 plus 6 is 16 IAs, 16 minus 6 IBs. So minus 6, so the IAs go in this column, IBs go in the second one. The second row is the second equation. Minus 6 IA plus 9 IB. So there's a positive 9 IB there. And IA and IB are what we're looking for. And this is equals 12, and this is equals 0. So this is how you set this up. This is called an incidence matrix, I believe, but the terminology regardless. But this is how you translate these two equations into matrix form. And again, I won't get into the details of that, but I do want to show you how does this mathematics work. And basically, we're multiplying this vector by this matrix, and we're coming out with another vector. How this works out is it's IA multiplied by its components, so IA times this vector, 16 and minus 6, plus IB times its components, minus 6 and 9. So you can see this and this is that incident matrix, and we just moved IA over here and IB in here. So we're multiplying that, and it comes out to the right-hand side, 12 and 0. Now, here's how you do the mathematics, and I chose an extremely simple one so you could actually see it. Now, you wouldn't be able to do what I call hand bombing this stuff too easy on anything difficult, which is why you always use software. But this one is simple enough that you can see what's going on. I'm going to show you here. So basically, 6 minus 6 and 12. We have to find a relationship here, and we have to find, using the same IAs and same IBs, a relationship that matches minus 6, 9, and 0. Okay, so what this is, if we chose, for example, I'm going to give you an example that's actually correct, but you'll see it this way easier. Let's just make IA 1. 1 times 16 is 16. Well, we know whatever this multiplies out to, it has to equal 12. Now, everyone understands this somehow has to work out to minus 4 then. So it's already minus 6. So what would we take to make this minus 4? Well, it would be 2/3. So 16 plus 2/3 of negative 6 is negative 4. Works out to positive 12. So 1 and 2/3. Let's see if 1 and 2/3 also solves this equation. So negative 6 plus 2/3 of 9, which is positive 6. Negative 6 plus positive 6 equals 0. You find your solution that way. That's how matrix math works. And you can see it in a very simple example like this. Generally speaking, anything real world, you would not see it that easily, and you would have to use software because it would be fraught with rounding errors and mistakes on your part. So nobody does it like that. Everyone uses software, and that is how computers calculate almost everything like that. You can just see how quick and easy it is. Not a lot of this stuff going on at all. We've already found the solution. So how a computer actually would do this, or how we would do this using a computer, is we would make what's called an augmented matrix. So we would stick this V onto the right-hand side of this R matrix. So I just put a little line here so you can see this is this incidence matrix, your resistance, your R, and this one over here is your volts. Now, this would require more explanation than this video can give. But essentially what you do is called row reduced echelon form, or simply called row reduction. And what you do is the top left and the bottom right on this little sub-index, these two, they are called pivots. What you want to do is make everything below the pivots 0. And it's easy to make the top ones. I won't get into that 0 after you've made these ones 0. So what you're trying to do is make this one 0 out. So in this column here, only this has a number other than 0. And in every example like this, you're going to be able to do that. There is going to be a solution. If there's no solution, you've either added information here that's actually incompatible with this circuit. You've made a mistake here maybe, but assuming no mistakes, there's always going to be a solution. And when there's a solution, you're going to get the left-hand side of this augmented matrix, 1s across the diagonals, top left to bottom right, and 0s everywhere else. That's your full reduction. And what you're going to do once you do that is this right-hand side, because whatever you do to this row here, to get this to 0 out by using row 1 here in this case, you also do to this number and this number. So you're going to be changing these numbers as these ones change. And again, this is not a linear algebra class, so I'm not going to show you that. But it wouldn't take long. Your first 3 or 4 weeks of linear algebra, you would be able to do this, right? But eventually what you're going to get is an identity matrix on the left. That's what an identity matrix looks like. And on the right, you're going to have your solution. IA is 1, IB is 2/3. You'll notice Wolfram Alpha gave us those exact same values. So look back over here on your diagram. If IA is 1 amp, what is I1? What is IT? It's also 1 amp. You can see those are put in there. Now, I2 needs special consideration again, because remember, what this is saying is if you've got 1 amp going this way and 2/3 of an amp going this way, so you subtract it, 1 minus the 2/3, and you get 1/3 of an amp, and it's actually going in that direction. Current is flowing in this direction. 1 this way, 2/3 that way is net 1/3 that way. That's how you get I2. And over here, IB, well, IB is I3. This is the only load with the full IB current. We don't deal with this one exactly that same way. So IB is 2/3. And if you'll look, that would be I3. I3 is 2/3. I2 is 1/3. And you have all the resistances, so you can very, very quickly calculate the voltages, just I times R. And you'll notice over here, we started with RT like we almost always do. We didn't have to do that because we knew VT was 12 volts. We calculated IA here, which is I1 and IT, as 1. So you didn't even have to calculate this. You just did VT over IT and you got 12 ohms. So you can see once you work this out, it was very, very simple, straightforward Ohm's law math. That's all you needed. And you can see it wasn't much different over here, except for the RT calculation. And if you're going to do it this way, you have to do the RT calculation first. Now, you don't have to, but then you negate doing it the way that you're generally taught first in your first electrical classes before you reach the advanced level math, which is, again, it's what engineers use, it's what software engineers use, it's how computers do it. Because this is the most robust way. You can imagine having a very, very complicated circuit here, how much difficult work, if you could do it all using this methodology. Whereas this methodology, you're simply making these matrices larger. You have more loop equations, but they're not much more difficult than this. And the answers just fall right out. And you are using software for this in all cases. And later on, I may make a video with an extra power supply in here. And that would be a great example of how you would have to do it using this methodology. And you really couldn't do it with this. I'm not saying it's impossible, but it would be impossible enough. It'd just be easier to learn how computers do it and do it that way. Significantly easier.